Okay, so let's get started, Matrix. It is 5 o'clock already. As we had discussed the previous time, you said you wanted feedback on the quizzes. So I have cut and paste the very last quiz that you did on not exponents, on functions and logs, and I have included it at the beginning today, so we can just quickly go through that before we get started on differentiation by first principles. I gave you this question, all right, which was the graph of, I don't know if it's easy enough for you to see it, was the graph of f of x equals log base 4x is drawn. And I told you that k was a point on this particular graph. And the first thing that I asked you to do was work out the value of k. So what I was asking you to do was to solve for the x coordinate, the input, when the output was 2. All right, so hopefully there you got 16 as your answer. Let's just go through how we would have actually done that though. All right, so we would have said for question 1.1, we would have said that 2 equals log base 4x. All right, and then if you have learned that little thing that I gave you, it becomes really easy to write this. 4 is our base, okay? So it's 4 is our base, 2 is our exponent, and that was equal to our number x. Okay, so therefore x was equal to 16. Okay, and then something like this would be worth 2 marks because there would be 1 mark for equating and another mark for the correct answer. Okay, then the second question is, what are the values of x for which f of x is greater than or equal to -1, but smaller than or equal to 2? All right, so for this particular question, again, there would have been a little bit of working out that was involved. Don't know if you remember, we'd actually gone through this question together in class. All right, so we know that when the input is, no, that's 16. Sorry, so k is equal to 16. Sorry, I said x is equal to 16, but it's the same thing, k is equal to 16. Okay, so what that means is that when your input is 16, your output is 2. Okay, so 16 goes in, and 2 is what comes out. So we already know where y is smaller than or equal to 2, right? Because we know that when x is a number that is smaller than 16, y is going to be smaller than or equal to 2. So essentially what we need to do here now is we need to work out where is it going to be equal to -1. All right, so what you would have done, similar story to the first question, is you would have taken -1 and allowed that to be equal to log base 4 to the x. Okay, so again, base to the exponent equals x, and that would have been where x was equal to 1/4. All right, so that would be, I guess, somewhere down here. We're saying 1/4 goes in, and we've got -1 coming out as our y. Okay, so that's why it would have been between where x is greater than or equal to 1/4, but smaller than or equal to 16. Okay, is that making sense so far? Any questions? Then the inverse. Okay, so if we are dealing with f of x being equal to log base 4x, our inverse is going to be y equals, let me just move this up, 4 to the power of x. So you should have chosen option I. Second to last question. In number 4, for which values of x, where x times f to the -1x are smaller than or equal to 0. Okay, so here we're asking you, where does input times output on the inverse, where is it going to be negative? So if we consider what this graph of the inverse looks like, all right, it would look something like this. So if I just quickly draw a set of axes, like so, our graph is going to be an increasing function. So it would look something like that, okay? And they're asking us where is input multiplied by output smaller than 0. So where is it negative? That's what the question is. So if we want to get a negative answer, because it's smaller than 0, we want a negative answer. So the only way we can get a negative out is when we multiply a positive with a negative. All right. So here we have to consider where we multiply a positive with a negative in order to get a negative, or we need to consider where we're multiplying a negative with a positive in order to get a negative. Now, the thing is that this over here, y, is always positive because it's always sketched above the x-axis. So that means we cannot consider this first situation. We can only look at this situation over here. Okay, where x is negative and y is positive. All right, so x will be negative up to this point over here. So when x is smaller than 0, a negative input times a positive output will give us a negative value. Okay, so that is why we had to choose K as our answer, where x was smaller than 0. And then the last one, they asked us a question about the range. All right, so the range is the set of output values. And as we have already discussed, your output values are always going to be greater than 0. So the line y equals 0 is the asymptote. So the range is going to be any value of y that is greater than 0. And that's why we would have chosen M as our answer, okay, for that particular question. Everybody happy with that? Any questions? Are we all good? All right, awesome. So let's not waste any time. Let's jump straight into calculus. Okay, so the first thing that I wanted to discuss with you is where the formula for gradient at a point actually comes from. And I don't want to spend too long discussing this because, you know, it's not the sort of thing that they're going to ask you. Your first question is going to be on first principles. But I think, like with anything, it's really important for you to be able to understand what it is that you are doing, right? So traditionally speaking, when we want to calculate gradient on a curve, all right, we would use gradient formula. So our bog standard garden variety, the gradient from A to B, so it would be this formula over here that I'm highlighting in blue. So the gradient from A to B is going to be the change in y over the change in x, right? So typically speaking, what we would do is we would say that if at A, if x goes in, and this is f of x, all right, then what comes out would be y or f of x. If we move our point h units to the right-hand side, it's now x plus h that is our input, which means that our output, our corresponding output, is going to be f of x plus h. So in other words, at point B, input is x plus h. Output is f of x plus h. At A, input is x, output is f of x. So when we want to work out the average gradient between A and B, we would just sub that straight into our gradient formula for how we would calculate the gradient of a line. So the y at B, this is going to be your y at B over here. That's why we're writing f of x plus h over there, minus your y at A, which is f of x. That's why that's been subbed in here, over your change in x. So x plus h, that's why we've written x plus h over here, minus x is going to be our input over there. And then at the bottom here in the denominator, because we've got x plus h minus x, it means that h is left on its own. And that's where we get f of x plus h minus f of x, all over h from. Okay, so it comes from gradient formula. When we are calculating the average gradient of a line, we are not working out the gradient at a point. What we are doing, it's like we are connecting point A and point B. Sorry, let me just try that again. The different color. We are connecting point A and point B. Let's just do that with it. Okay, and then I'm just going to move this line a little bit. So in other words, it's like me connecting A and B with a straight line, like the orange one that I've done there. And I'm working out what is the gradient between A and B. That's what average gradient is, all right? But it doesn't tell me the gradient at a particular point. And that's what calculus is all about. It's all about determining the change at a particular point in time, all right? So we move from average gradient, our typical gradient formula, to gradient at a point, right? Now, I've explained to you where the f of x plus h minus f of x over h part comes from. The rest of this, we need to understand calculus. Oopsie, sorry, I'm highlighting in the wrong color here. The rest of this, we need to understand a little bit about calculus to understand what that means and to understand what this means. Okay, so the first thing that I want to talk about is your limit as h approaches 0, which is how you would say this. Okay, so this bit over here, we would say this is your limit. Limit as h approaches 0. Okay, so what we are doing is we are moving point B back down towards A. So what is happening if we want to measure the gradient at A? So in other words, if I have got my set of axes and there's the one arm of my parabola that I'm looking at, B was somewhere over here and A was somewhere over there. So what starts to happen if I want to measure the gradient at A? B is moving back down towards A. That means that the distance between B and A is getting smaller. So in other words, if here at A, X is what went in, and over here at B, I'm now at X plus H because I've moved H units to the right-hand side. This is why we say that H is approaching 0, because the further to the left we go, the smaller the gap becomes between A and B. So this value of H here is approaching 0 as B travels back down towards A. What we want, of course, when we are measuring gradient at a point is that we want to figure out what the gradient at A is going to be. So I don't want to work out the gradient between the points. I want to know what is the gradient at A. The problem, of course, is that as H approaches 0, if we use traditional methods and we say that H is 0, what's going to happen to this formula? It means that everything is going to be divided by 0. And if something is divided by 0, then mathematically it would be considered to be what matrix?
Undefined.
It would be undefined. It would be undefined. Okay, so that's why we cannot divide by 0, okay, because it would be undefined. And that's also why we cannot write that H is equal to 0 either, okay, because we cannot ever have division by 0. And this is why, who it was actually Isaac Newton that figured all of this out. What he did was so very, very clever, because what he did is he said, in order to get around this problem of division by 0, let's take this straight line. What we can do is we can work out the gradient at a point by drawing, me just try and move this line a little bit. By drawing a tangent to the function at that point and then measuring the gradient of the tangent. Okay, so that's actually what we are doing when we are measuring gradient at a point. Okay, so that's what this bit means. All right. This bit in the front, this f prime x, is the notation that we use to show that we are determining the derivative or the gradient or the instantaneous rate of change. So if we have been given a function statement in the form of f of x, then we would take the first derivative, we would write f prime x like so. Okay, very important when you're doing gradient from first principles, you cannot drop the limit notation until you are ready to sub h equals 0 in. But of course, we don't do that. We don't show that part. And they will penalize you if you drop your limit notation. They will penalize you if this h mysteriously disappears and then reappears towards the end, which is a lot of matric students make that mistake. But it's normally only 1 mark that they would penalize you. But I mean, of course, we don't want to lose any marks at all. Okay, so let's show you an example of an exam question. Oh, and what I was trying to show you here is how, if we now want to measure the gradient at A, it's like us drawing a tangent to the function at that point, and the gradient at that point is going to be f prime A. Okay. All right, so first up is this one. Okay, this comes from the 20, I can't remember where I stole it from. 2021 or 20, yeah, I think it was the 2021 paper. Okay, pretty typical question. All right, your formula is going to be on your sheet. All right, so all you need to do is sub into it. This is how I teach my classes. I teach them to first calculate f of x plus h, the difference between the two, and then sub that in. Okay, because that's what you're subbing into the numerator, is the difference between f of x plus h minus f of x. So this is how I teach my classes to set it out. Okay, we've got f of x equals 1 minus 3x squared. That means that f of x plus h is 1 minus 3x plus h squared. Now let's remove our brackets. This is just normal grade 9 multiplying out. So we're going to have 1 minus 3. When we square our binomial, remember, it's square double square. Okay, so it's going to be x squared plus 2xh plus h squared. Get rid of the brackets and we will end up with 1 minus 3x squared minus 6xh minus 3h squared. And then, in my opinion, the easiest thing for you to do next is to say f of x plus h minus f of x equals 1 minus 3x squared minus 6xh minus 3h squared minus. Now, what you can do here is you can put f of x in brackets. But if you want to save yourself a little bit of time, and f of x is a binomial, which it normally is, you can just change the signs. So in other words, 1 is going to become a negative, and 3 is going to become a positive. Does everybody understand what I've done there?
Yes, ma'am.
Sure. It just saves you another line of writing out. Okay, and then what we should find here is that when we are saying f of x plus h minus f of x, anything that doesn't have an h in it should cancel out. It should be an additive inverse. It should add up to 0. Okay, because what we want is something that has an h in it so that we can factorize. So 1 minus 1, that means that the 1's are gone. 3x squared minus 3x squared plus 3x squared means that that's gone. And what we are left with is minus 6xh minus 3h squared. And now that is what we can take and sub into our first principles. All right, so we will write f prime x is equal to the limit as h tends to 0 of minus 6xh minus 3h squared all over h. Now, of course, we need to get around this problem that h is tending to 0. Okay, we cannot show that h is 0. We're not allowed to do that. So how we get around this problem, so clever, is we factorize and we take h out. We only ever have to take out h. And inside our brackets, we've got minus 6x minus 3h. You should then show that the h at the top and the h at the bottom now cancel out. If you want to, you can include an extra line here if you wish. So you are able to write equals your limit as h tends to 0 of minus 6x minus 3h. Or what you can do is just go straight to the answer. Okay, so in this case, it would be minus 6x. Right, so I do not show that h is 0, but essentially what we're doing here is that we're subbing in our heads, right? So this term over here becomes 0, but I'm not allowed to show it. Is everybody happy with that? Okay, sure. All right, now, I know that I've done that quite quickly, but it's just because normally first principles are something that a lot of people get, and I don't want to waste your time going on and on and on about it if it's something that you actually understand pretty well already. Okay, of course, once you've got to the end of calculus, you will know how to get the answer using the power rule, but that's not the point, okay? The point is, and every single paper is going to have one of these, and I'm sure your teachers have told you that. So you will always be asked to find the derivative by first principles. It's always the very first question in calculus, generally worth anywhere between 4 and 6 marks, depending on how labor intensive it is. All right, so you can see with this one here, this one, oh, did I chop off the marks? I think that was out of 5. This one over here, that's why I wanted to include the marks for you. Right. This one is also out of 5 in this case. All right, so if there are no questions, then let me copy and paste this for you guys as well. All right, there we go. So you guys can do this one. Okay. And then we'll look at the answers afterwards. Okay, so Nicole and I are just going to be quiet for a little bit, Matrix. You work on that question. Please ask if you've got any questions, okay? Cool, can you see there? Lovely. Good, Tisha. Nice. Cool, Neo. Well done, Thelma. Okay, and of course, the quicker you can do this, I mean, obviously you want to do it accurately, but the quicker you can do this, the quicker you can move on to the other questions in calculus, as well as spend time on sort of more problem-solving sorts of questions. So yes, this is meant to be easy and simple and quick. Lovely. Well done, Oratile and Njubulo. Nice, Lesedi. Okay, so I'm just going to wait 1 more minute and then I'm going to go through the answers. Okay, let's have a look at the answers now. Oopsie, sorry. Why did I do that? There we go. Come here. Okay. So you can see what the 5 marks are for. Okay, so a mark for subbing in your x plus h, a mark for working out the difference between f of x plus h and f of x. Oh, sorry, it's working out f of x plus h. It's just so much easier to work out the difference and then sub that in. You have to show that you factorized and cancelled. And again, if you want to show this step over here, you can. This one, let me just highlight it in yellow, this step here. But if you don't show that step and you go straight from here to your answer, that's also okay. All right, so you're not going to get marked down if you don't show the step that I've highlighted in yellow. Any questions? Is everybody all right with that? Okay, and then here, I don't suppose, let's just see if it's okay, so Nicole just asking you guys again if you're okay. I had got another one, but I don't think we need to do that. I think you guys are probably all right. What I did want to show you. Nice. So did everybody get it right? So Mighty says yes. Anybody else? You all get it right? Cool. Good, lovely. Okay. Do you think we need to do another one or can we move on? You can pop it into the chat. So another one or move on. Cool. Lovely. Fabulous. Okay. All right, so most people are saying move on. Emily, if you need more practice, there are loads online under the Department of Education website. So go and have a look online. All right, it's the easiest place to find these questions. Okay, let's move on then. All right, so now I want to spend a little bit of time talking to you about exponents and surds before we jump into the basics of differentiation using the rules. Okay, and The reason for this becomes apparent when we learn how to apply the power rule. So whatever they give you, you need to be able to write it in a certain way, all right? And the way that you need to be able to write it is like this, okay? You've got to separate the coefficient. Okay, so you've got your coefficient at the front. Then you have your variable, and your variable needs to be in the numerator. And then you've got your exponent over there. So every single term has to be written like this. So essentially it's sine, coefficient, separated from the variable in the numerator with your exponent. And if you can do that to every single term, that's when you are then ready to start differentiating. Okay, so now they don't always give things to you like that. So they would expect you to be able to do that. So let's just go through some rules first. So if they give us x to the power of 9 over 5, if we want to separate the coefficient from the variable, we would write it as 1 over 5, x in the numerator to the power of 9. Do you see what I mean? So plus sine, coefficient 1 over 5, x in the numerator, exponent is 9. Then if they give us something like 3 over x to the power of 2, it's our job to move something from the denominator into the numerator. So if you recall from grade 9 is the first time you do it, grade 9, grade 10, grade 11, we know that we are allowed to move a variable from the denominator to the numerator if we change the sign. So this would be 3 over 1, which should be written as 3, x into the numerator, and change the sign of the exponent. Is everybody happy with that? Very, very important. Okay, then if they gave you something like this, 2 over 3x to the power of 4, the number doesn't want to be an exponent. It's the variable that you've got to move. Okay, so it doesn't matter if you've got a number in the denominator, it's the variable that can't be in the denominator. So you will leave this coefficient as 2 over 3. Take the x up to the top, change the sign of the exponent. Does that make sense to everybody? Yes, or they could give you, they could be a little bit meaner to you, and they could give you something like this, where they give you 8 over 3x, and then they square it. So the easiest thing to do there would be to square your denominator first. This would give you 8 over 9x squared. Oopsie daisy, I'm writing so fast I'm making a mess. 9x squared, and now you can separate your coefficient, take your variable to the numerator, change the sign of the exponent. By the way, with all of these that I've done so far, if they gave you something like 2 over 5x to the minus 3, not that you generally see that, you wouldn't, but this you would write as 2 over 5, take the x to the top, and change the sign of the exponent. So if the exponent is negative whilst it's in the denominator, it needs to be negative in the numerator. If the exponent is positive in the denominator, it needs to be negative when it gets moved to the numerator. And similarly, if it's negative in the denominator first and gets moved to the numerator, it would also change its sign. So just be aware of that. Okay. Then when they give us roots, okay, so a good place to start with this, if you want to understand what it is that we're doing, actually goes all the way back to grade 8. So in grade 8, you get taught to answer questions like this. So 16x to the power of 4. Do you remember that? All the way 5 years ago. So it was one of the things you would have learned how to do in algebra. And hopefully what your teacher would have done is your teacher would have explained to you, well, this means we've got to break 16x to the power of 4 down into two things two values that when I multiply it by itself, I'm going to get back to my 16x to the power of 4, right? So the 16 is the easy part. That we can do on a calculator. We shouldn't need to, but we could. But what happens to my exponent? So any number that is a multiple of 2 that is even is also going to be a perfect square. Okay, and that's because x to the power of 2 multiplied by x to the power of 2, when we multiply this by itself, we keep the base, we add the exponents. Okay, so what I'm trying to say to you is if I take the square root of x to the power of 4, I get that. So what I'm essentially doing to my exponent here, matrix, is I am dividing it by 2. That's where this 2 comes from. Okay, because 4 divided by 2 gives me 2. All right, so this would be 4x to the power of 2. And that's because 4x to the power of 2 multiplied by 4x to the power of 2 gives me 16x to the power of 4. All good. Okay. So similarly, if they ask you to work out the square root of 25y to the power of 12, what would our answer be? Does someone want to tell me? Exactly. Okay, so it would be 5y to the power of 6. Okay, because if we multiply that by itself, we would get 25. So now that we're all 100% with that, what happens if we're talking about a cube? So now if I have got 27x to the power of 15, and now I'm taking a cube root. With a square root, I divided the exponent on my variable by 2. With a cube root, I've got to divide the exponent on my variable by
3.
By 3, exactly. So the cube root of 27 is 3. Careful, it does not mean 27 divided by 3. And now if I take my 15 and I divide it by 3, I'm going to end up with 5. Okay, and similarly, that is because 3x to the power of 5 times 3x to the power of 5 times 3x to the power of 5 is what's going to give me my 27x to the power of 15. So this is what I teach my boys at school. The guy on the outside, okay, he's the one at the bottom. All right, so the guy at the bottom gets kicked to the outside of the party. So in other words, you are now dividing that 15 by 3. So the guy at the bottom is the one that gets kicked to the outside of the party. Okay, so when you're working back the other way, if they give you something like this, heaven forbid, okay, the guy at the bottom gets kicked to the outside of the party. So that means that if we now want to write this without the root as a rational exponent, we will write this as x to the power of 2 over 7. Okay, so the one at the bottom gets kicked to the outside of the party. Everybody happy with that? Okay, it's just a stupid way of being able to remember these things, but if we can do that, then it helps us. Okay, so to cut a long story short, if they then give us, let's just get rid of all of this writing here. If they give us 5 over the cube root of x squared, okay, we know that the 5 is in the numerator, that's fine. So this is going to be 5 over x to the power of the guy on the outside gets killed. The guy at the bottom gets kicked to the outside. So that would be 2 over 3. And now when we take it up to the top, we would write that as 5x to the power of minus 2 over 3. Okay, be very careful how you write your exponents. Make sure that you are writing it as an exponent. Okay, so give yourself lots of space. Don't squash things all together. You basically want to make it as easy for your marker to see what you're doing as you possibly can. All right, and then if they did give you a strange situation like this last one, where they have given us the cube root of 6x to the power of 5, we can't write the cube root of 6 in any other way, so we would have to leave that as the cube root of 6. And then as far as our x is concerned, we would write that to the power of 5 over 3. Okay, do you guys feel that you need to practice some of this, or can we move on?
Is it negative exponent?
No, the exponent is not negative because here your x is in the numerator.
Oh, right, sorry.
Okay, because that's over 1, yeah. But thank you for checking because I do make mistakes. All good. Okay, so can you see Les saying we can move on? Okay, thank you, Thelma. Okay. So move on, move on, move on. All right, fine. Okay, so the other thing that I wanted to spend just a little bit of time talking about is the importance of notation. Okay, and I'm sure that your teachers at school have stressed this to you as well. Okay, matrics, if you mess up the notation, they are going to penalize you somewhere for it. Okay, so it's not the maths that you are writing, but it's also the way in which you are writing the maths that is so important. Okay, so be very, very careful about your notation. The 3 most usual forms are this, right? So if they give you your function in the form of f of x, you will write your derivative in the form of f prime x. Okay, you will only write f prime x in the line where you are applying your power rule. Okay, so if there is a little bit of work to be done before you apply your power rule, you cannot write f prime x. Okay, very, very important. Okay, if you are given your function in the form y equals, then you will write your derivative as the derivative of y with respect to x. That's what that dy over dx means. Okay, the derivative of y with respect to x. And you can only differentiate any function statement with respect to one variable at a time. But we'll talk about that a little bit more in the coming lessons. All right, so dy over dx. And again, you only write dy over dx when you are applying your power rule. If you're doing some work, you're preparing your statement for differentiation, you cannot write dy over dx, dy over dx, dy over dx. It's only in the line where you apply your power rule. And similarly with our dx and our square bracket. Okay, so this is another way in which they love to give things to us. They write it like this, so dx. And now when we write our derivative, what we do is we drop the dx, we drop the square brackets, and we just write the equals. That then tells the person that is marking our work, all right, that we are applying the power rule. Okay, so be very, very careful because they do penalize for notation. All right. Any questions about that? A little bit. No, we all good? Okay, so now, when it comes to differentiating, there really are only 2 rules in differential calculus that we need to pay attention to. The first one is that the derivative of a constant is equal to 0. So in other words, if you have got f of x equals 3, what does that mean? I mean, if I was to draw a graph of f of x equals 3, what would my graph look like? It's going to be a horizontal line, okay, that goes, oh no, come on, you are not serious. Okay, I don't know what I've done again, but for some reason I'm not sharing my screen. Just give me 1 second. Don't know what it is that I press here that it doesn't like. Sorry guys, just give me 1 second. Just taking a little bit of time to come up. Okay, got it back. Here we go. There we go. All right, hopefully we're back in business. Okay, so if we have f of x equals k, where k is a constant real number, what we are saying is that the derivative, the gradient at the point, is always going to be 0, okay? Because if I am standing over here and I walk in that direction to a point down there, I have not walked up. I have only moved in terms of x. I have not moved in terms of y. So any line that is parallel to the x-axis has a gradient of 0. Remember, f prime x means the gradient. So the gradient of any horizontal line is always 0. That's what rule number 1 means. The second rule, the power rule, is our shortcut way of, there we go, of determining the derivative, okay? And as I'm sure a lot of you are aware by now, we determine our first derivative by multiplying the exponent by the coefficient and then taking 1 away from the exponent. That's why it's so important that we do questions like this and we know how to write it as a coefficient variable in the numerator and then our exponent like that. So the power rule, if I wanted to now apply my power rule to one of these, okay, so let's say I had y equals x over 9 to the power of 5. Bearing my, okay, so now take note of the notation. I'm not deriving. I'm preparing my statement for differentiation. So I'm separating my coefficient. I'm putting my x into the numerator, what it was in the numerator. Now I'm ready to derive. Because my coefficient is separated from my variable is in the numerator, and I can see what my exponent is. So now if I've been given y, I'm going to write the derivative of y with respect to x equals. And now when I apply my power rule, I'm taking 9 and I'm multiplying it by 1 over 5. So 9 times 1 over 5 is 9 over 5 x. Take 1 away from the exponent. It's going to become 8. Okay, so it's not just the maths, it's how you write the maths as well. Okay, everybody happy with that? So if they give us f of x is 2 over 3x to the power of 4, okay, I cannot write f prime x until I apply the power rule. The power rule is when you are multiplying the exponent by the coefficient and taking 1 away, all right? So I still have to write f of x until I'm ready. Separate the coefficient, take this into the numerator, change the sign. Now I'm ready to apply the power rule. Coefficient, variable in the numerator, exponent. So here you've just got to be careful of your grade 8 maths. Okay, so a positive times a negative is a negative. So this will be negative 8 over 3 x to the power of negative 5. All right, when I take my derivative, so f prime x. Is everybody happy with that? So it's not just what you are writing on the right-hand side over here, guys. You also have to pay attention to your notation as well. Sorry, I'm doing this quite quickly. Is everybody following me? Any questions? Happy, cool beans. Sure, guys. All right. Cool. Where are we? Okay, so there we are. Okay, so functions with one term, I would think, I mean, we've got to start somewhere, right? So that's why we would start with something. Why is that there? Oh, I think because that was something that was a little bit further on. Okay, so functions with one term are really very simple, and I'm sure you would get that in a class test or in a control test. Maybe they would give that to you as a simple question, but that's not generally the sort of thing that you're going to see in the exams. All right, so I think as far as all of these ones are concerned, this is pretty easy, isn't it? I don't need to go through 6 times 3 is 18, take away 1 is 5. Is everybody happy with that? Okay. If they give you y equals 2x, all right, and now they ask you to take the derivative of y with respect to x, remember, it's going to be the invisible 1 times 2. And then remember, when you take 1 away, you're going to end up with x to the power of 0. Okay, so x to the power of 0 is 1. So essentially what you've got here is 2 times 1. All right, but you don't have to write that. Okay, and what we're saying is that the gradient of a straight line, the line y equals 2x, we're saying the gradient is 2. Okay, and you know that anyway, because y equals mx plus c. You know that m, the gradient, whoops, yeah, I didn't mean to rub it out. You know that the gradient is 2. Okay. Can you see that's just what they have discovered works in this particular instance. Okay, so we're always going to be subtracting 1 from the exponent. People that have sort of studied maths and discovered all these rules have worked this out. All right, so it only works when we take 1 away from the exponent, never if we take anything else away. Okay, but yeah, it's all through. So maths has kind of been like it's partly the fact that it's always been there and always existed, and it's also partly been created by us. So this is just one of the things that people have discovered in the study of maths over the years. Okay, all right, so let's rather go and have a look at something like that. Okay, when we are differentiating, right, we have to remove, how much time have we got? 5 minutes. We have to remove, okay, number 1, divide lines. Okay, so again, it's okay if the number's in the denominator, but we don't want the variable in the denominator. So when I say remove divide lines, I mean removing that. So in other words, 3 over 2x to the power of -4, we've got to remove divide lines. Okay, so the divide can be here, but the variable's got to be in the numerator. Number 2, we need to remove roots or radicals. Okay, so something cannot be written in third form like it is here. We have to write it in with rational exponents. So write with rational exponents. And then the third thing that we need to remove matrix are brackets. Okay, so this is some of the work that needs to be done before we can differentiate. So if we look at example number 6, what we would want to do, first of all, is keep our notation because we are not differentiating just yet. I'm going to put the 2 at the top. The cube root of 27 is 3. And of course, when I take the cube root, I divide my exponent on my variable by 3 as well. I'm going to end up with that. I'm still not ready to differentiate until I have removed the divide line and written the x in the numerator. So I'm going to keep my notation as it is. I'm going to pull 2 over 3 off and separate my coefficient. X goes into the numerator and I change the sign. Now I am ready to differentiate. Hold on a moment, getting these guys out of the way. Now I'm ready to differentiate. So remember, when I am using this kind of notation, that's like this one here that's highlighted in turquoise, I show that I'm applying the power rule by dropping the dx and the square brackets and just writing equals. And now I'm going to say -3 times 2 over 3 is going to leave me with -2. X to the power of, take 1 away, -4. And that's it. Okay, in matric, you are allowed to leave things with negative exponents. You don't get any marks for making it a positive exponent, so don't even bother. Just leave it with a negative exponent. Okay. Is everybody happy with that? Any questions? Happy, cool beans. All right, nice. Lovely. All right, everybody. Okay, so that means that next time we'll start here and we'll jump straight into what happens when we've got a monomial denominator and when we've got a binomial denominator, etc., etc. Okay, we'll see you guys next time. Thank you so much, Nicole, and thank you, grade 12s. Please do the poll before you go. Thank you.